And he'll be talking about verifying the Vickrey Clark growth mechanism. Thank you.
So, good afternoon, everyone. I'm here to present our project, which applies the RocqPL' theorem prover in formalizing the mechanisms from the auction theory. And I am Zhan from Shanghai Jiaotong University. I'm currently a master's student, and the project is collaborated with Professor Pierre Jouvelot from Paris. The type of auctions that we study today is called the sponsor search auctions, which describes the scenario where multiple sellers compete with a process of auction in order to determine their position of attractivity on the web page when a relative keyword is entered by the web user. For example, in this picture, we illustrate an example of the Google search engine, and the keyword entered is about the cars, so that the sellers will show up as the slots, each linked to their information on the website. Different from the well-known auctions, where it is implemented in a public auction house, and the auctions bid in multiple turns. The cell-bid auctions is implemented through a private protocol, which means that the agents or the bidders cannot see the bidding values from the others, and which is different from the artwork. And the only one who can see all the bidding values is the auctioneer, and she's responsible for allocating the items to each bidder and then determining the corresponding price. So before detailing about the sponsored auctions, I would like to introduce a little about the motivation in studying the auction theory. The auction theory is a branch of the algorithmic game theory, and we start with a simple case where there is a single item, and a natural strategy for the auctioneer is called the first price mechanism, where the highest bidding agent gets the item and is asked to pay the price that she bids. However, this does not generate a stable strategy for the agent, because the winner would always like to underbid in order to get the item with more money. A better strategy is called the second price mechanism, where the agent can get the item with her highest bidding and is asked to pay the second highest price. In this case, a great property is guaranteed, where the truthful bidding, which means that to pay her highest affordable price, is the best strategy for each agent. Since if she underbids, she will always have to pay the second highest price. And instead, if she overbids, and by coincidence, there is another agent that has a price which is over her highest affordable bidding price, but is lower than her overbid price, then she has a risk of losing money. And the economic theorists find this property with the mechanism interesting and would like to extend it to the case with multiple items. However, it does not work by simply allocating a higher bidder to a better item and ask them to pay with the bidding price right after theirs, which is as known as general second price. This does not guarantee the good property. The case that it works is called the general VCG, Vickrey Clark growth mechanism. And in this kind of mechanism, each agent is asked to determine a price over a combinatorial subset of the items. So that, of course, it is a general case of the sponsor search auctions. And in reality, there are platforms that runs on a version of the sponsor search auctions and is announced by the theorist to be a specific version of the general VCG applied in sponsor search. And however, it runs with a complete different algorithm with the general VCG, and this is where our interest lies. That is to verify this with the formalization tools. So we come back to the main notions in the sponsor search auctions, where there are multiple agents and who bid for the multiple positions. And for each auctioneer, she's responsible for allocating each agent to at most one slot. And in each as agents, there are always more agents than the number of slots. And for each agent, there are some notions related. She is asked to bid a fixed price, which reflects her expected payment for a click by the web user. And the valuation is a notation for her highest affordable payment per click. And the real payment is determined by the auctioneer. And for each winner, her utility is determined by the difference between her valuation and the payment. And if she loses, her utility is 0. And for each slot, there is a percentage related, which reflects the attractivity percentage of the slots compared to the other slots. So it is better to describe with a picture, with an example. So there are 5 agents, and which bids from higher to a lower price, and is allocated to the better, to the worse, or to the worse slots. From here, we already have seen the problem of the nuanced problems, which is there might exist people with equal biddings, but they can be allocated to the distinct slots, and there may exist slots with the same attractivity, but they are allocated with the different bidders. And we ask in the current version that if this property in the sponsor search auction is so guaranteed, and the final payment from each bidder is determined by the user. That means if the web user clicks on the click-through rate, then the bidder have to pay for it. So the VCG mechanism for sponsor search guarantees 2 important properties. The first is it maximizes the social welfare, which is a function that sum over the bids that wins in the auction. So by intuition, we know that this can be realized with a sorting algorithm. And the second one is the interesting one, we have talked about it, is that bidding once valuation is the best strategy for each agent. And on this situation, we call that it is a truthful agent. And in reality, the VCG version for sponsor search is implemented through a sorting algorithm. And the general VCG is implemented with a searching for arguments that maximize the social welfare function. They are implemented completely differently, and we want to formalize that they are equivalent. So the concerns is theoretically VCG SS is a direct application of general VCG, and algorithmically the cases with equal bidding case might influence this kind of equivalence. We implement with RocQ. The first is we parameterize over the tie-breaking functions in general VCG, so that in each kind of tie-breaking way, which means to choose each kind of combination as the outcome, the property of the general VCG is always guaranteed. And for each agent, her utility is guaranteed under each equal bidding cases. And the proof approach we use is functional, which means that we abstract the general VCG as a function with the parameters, including the tie-breaking ways, including the social welfare functions, and we pass the structures of VCG as the values into the mathematical terms of the general VCG in order to get the equivalence. The repository on GitHub is called Mike.V. It is the certified library for auction mechanisms from 3 parts. Firstly, it determines the core definitions for auctions and specifically for sponsor search auctions, including whether each agent is a winner and the price utility related to hers. We have a dependency of the classes of distinct mechanisms. Relatively, the bubble sort is independent file that determines the bubble sort, which constructs a link between to maximize the social welfare function and the bubble sort, that each time with the sorting algorithm we can get the the social welfare function larger. And the MEC.V is an abstract structure over all kinds of mechanisms, including not only auctions, but also matchings and voting mechanisms in game theory. And the VCG folder includes the files including the general VCG, the VCG versions for sponsor search, and how we structure them together. And in the current version, we move the hypothesis where the tuple of bits and the tuple of click-through rates must be unique, which is always eliminated or simplified as the true in the economic theory. And we formalize the properties, including that in each kind of combination, the general VCG is always truthful, and that's how we pass the values from the VCG as into the truthful VCG to get the equivalence between the price. So the things that we would like to talk about is firstly the necessity of introducing the argmaxes when we use the general VCG with multiple combinations, because when there are multiple combinations, the argmax is arbitrarily, and we would. So we stop here with contributions, and I'm happy to wait for your questions.
Does anyone have any questions? Just raise your hand and we'll bring you a microphone.
So what are the background theories that you rely on?
The background theory about the formalization is the auction theory.
But in the formalization?
The ROC implementation with the proof approach that is functional.
Okay. I have a second question. Why is it important to work on bubble sort?
Since it is that in the general VCG, we would like to find the argument that maximize the target function, which is here the social welfare function. And in sponsor search, the larger bidder is allocated to the higher click-through rate, so it is implemented with a sorting algorithm. And the bubble sort algorithm is used to verify that when we swap each pair of bidders, the larger bidders allocated to the higher click-through rate can realize that the maximum social welfare function is reached.
So it's important because you have a specific look at pairs of bidders.
Yes.
You seem to have spent a lot of energy dealing with breaking ties.
Yes.
Is this correct? In other algorithmic endeavors, like when you work in geometry, when you have this kind of difficulty, people introduce infinitesimals, and then they break the ties because nothing is equal to things are no longer equal, right? Would that have been possible in your case?
We haven't thought about this kind of solution. And in our case, when there is equal biddings, so there are a set of arguments that maximize the case, and also in the sponsor search with the sorting type, there is multiples. So we can only guarantee that for each singleton that is chosen by the sorting algorithm, it corresponds to a solution in the general VCG, and the property is guaranteed.
Can the next speaker come up? While we're doing that, we have time for one more question. If not, let's thank our speaker again.
Yes, thank you.